We're asked to find the smallest angle of a 2, 3, 4 triangle. This picture is drawn roughly to scale. It turns out the smallest angle of a triangle is opposite of the smallest side. If you didn't know this, or it didn't occur to you, then you would have just found all three angles of the triangle and just decided which one was smallest after having found them all. But I can save time by just finding the one opposite the smallest side. To do this, I decided to use the law of cosines. And the law of cosines is something that I use whenever I don't know that I have a right triangle, and this one isn't. And when I have anything other than all of the angles. In other words, I only use the law of sines when I have all the angles. So to use the law of cosines, I decided to set up my equation this way. Remember that the side you start with, notice I started with the 2. The side you start with must oppose the angle you end with. And since it's theta that I want, then I have to start with the side length 2 to properly use the law of cosines. At this point, it's pretty much pure algebra. Exponents and multiplication, combining like terms, isolating the cosine, and hit pause if you want to analyze the algebra. At this point, I'm going to do something that you generally cannot do. You generally cannot bring a cosine over as its inverse or inverse cosine in this case. There is an exception to this rule, though. You won't lose any solutions to the equation when you do this, as long as you know that theta, or the angle you're looking for, is between 0 and 180, or between 0 and pi in radians. And since we know that theta is between 0 and 180, it is, after all, the angle of a triangle. It certainly couldn't exceed 180. Then it's safe to assume that I can bring the cosine over as an inverse cosine without loss of any valuable solutions. At this point, you would type that into a calculator and get about 28.55 degrees, or rounded 29 degrees. And that completes the fourth problem.